Hi everyone, this is NLP Corgi. Today's deep dive is about the paper from Google Context Engineering, Sessions and Memory for LLM Agents. Large language models don't actually remember anything between calls. Each request is a blank slate, limited to whatever you pack into the context window. But real applications need continuity, remembering who the user is, what they did last time, and what's going on right now. This white paper argues that two concepts, sessions and memory, are the foundation for turning raw LLMs into stateful, intelligent agents that feel persistent and personal. Traditional prompt engineering is about writing a really good, often static prompt. Context engineering zooms out. It's about constructing the entire payload for each turn: instructions, tools, history, external data, and user input. The job is to dynamically choose, compress, and format just the right information so the model has everything it needs and nothing it doesn't to solve the current task. Think of the context as a carefully packed suitcase. First, you add guidance, system instructions that define the agent's persona and constraints, tool definitions it can call, and a few examples to shape its reasoning. Then you add evidence, long-term memories, retrieve documents, tool outputs and results from sub-agents. Finally, you ground it in the present with the recent conversation history, any working scratchpad state, and the user's latest question. Context engineering is the discipline of deciding which of these pieces to include on every turn. On every turn, an agent runs through a context management loop. First, it fetches context, user memories, retrieved documents, and recent conversation events. Next, it prepares the context, assembling a full prompt that's ready for the LLM. Then it invokes the model and any tools, often in multiple steps, appending outputs back into the working context. Finally, it uploads new information to persistent storage, updating the session log and generating or refining memories, often in the background so the user isn't kept waiting. You can think of a session as a workbench for a single conversation. It holds every turn of dialogue plus any temporary state the agent needs right now. Memory is more like a filing cabinet. After the work is done, you don't store every scrap of the workbench. You extract the key facts, summaries, and decisions and file those away. Sessions are the raw, noisy source. Memories are the cleaned, durable knowledge that can be reused across future conversations and even across different agents. A session is the container for one continuous conversation with an agent. It's tied to a specific user and acts as a chronological log of events, user inputs, agent responses, tool calls, and tool outputs. Alongside that log, there's often a state object, a structured scratchpad that tracks things like a shopping cart, intermediate calculations, or task progress. As the conversation unfolds, new events are appended and the state can be updated according to the agent's logic. Most production agents run in stateless environments. Each request starts fresh. To maintain continuity, the full session history has to be stored in a persistent database or a managed session service. In development, you might keep everything in memory, but that doesn't scale or survive restarts. In production, you need durable storage that can reliably load the session at the start of each turn and append new events as the agent runs. Agent frameworks sit between your code and the LLM APIs. You work with higher-level objects like sessions, events, and messages. Under the hood, the framework converts those into the exact request format the model expects. For Gemini, that's a list of content objects with roles and parts. This abstraction lets you write your agent logic once, while the framework handles the messy details of different LLM providers and their evolving APIs, helping you avoid vendor lock-in. Different frameworks implement sessions differently. In Google's ADK, a session object explicitly holds a list of event objects plus a separate state object. It's like a filing cabinet with one folder for history and another for working memory. In LangGraph, there's no separate session object. The state is the session. That state includes the message history and all other working data, and it's mutable. LangGraph can transform or compact this state over time, which is especially useful for long-running conversations under tight token limits. In multi-agent systems, you don't just have one agent, you have a team of specialized agents working together. For them to collaborate effectively, they need a way to share what's happening. The persistent session history is the full transcript of all interactions, but that's different from the context you send to the LLM on any single turn. An agent might only pass a filtered slice of that history to the model. When we talk about multi-agent session patterns, we're really talking about how agents share and interpret that underlying history, not just the prompt they send to the LLM. There are two main ways to manage session history in multi-agent systems. In a shared history model, every agent reads and writes to the same conversation log. This is ideal when agents are tightly coupled and need a single source of truth. For example, in multi-step problem solving where one agent's output is directly another's input. In a separate histories model, each agent maintains its own private log. Other agents only see explicit messages, not internal reasoning or tool calls. This black box style is useful when you want modularity, encapsulation, or clear boundaries between agents. When agents keep separate histories, they still need a way to talk. One approach is agent as a tool. You invoke another agent just like you'd call an API, passing inputs and getting back a final output. Another is an agent-to-agent, or A2A protocol, where agents exchange structured messages directly. In both cases, the receiving agent doesn't see the sender's internal steps, only the inputs and outputs that are explicitly shared. Abstraction is a double-edged sword. The same internal data structures that decouple your agent from a specific LLM also tie it to a specific framework. Once you persist sessions using that framework's schema, other frameworks can't easily read them. A LangGraph-based agent can't natively interpret ADK's session and event objects, and vice versa. That makes seamless task handoffs across frameworks difficult unless you build custom translation layers. Agent-to-agent protocols help agents exchange messages, but they don't solve the deeper problem of sharing rich, contextual state. Each agent's session history is locked into its own internal schema. The paper proposes a more robust pattern. Abstract shared knowledge into a framework-agnostic memory layer. Instead of raw events, you store processed information, summaries, entities, facts, in simple, portable structures like strings and dictionaries. This shared memory becomes a universal cognitive resource that heterogeneous agents can all read and write, without bespoke translators for every framework pair. In production, session management isn't just a convenience. It's a security-critical service. Each session must be strictly isolated, so one user can never see another's data. Every read and write to the session store needs proper authentication and authorization. On top of that, personally identifiable information should be redacted before it ever hits storage. Tools like PII scrubbers or model armor can drastically reduce the impact of a breach and make compliance with regulations like GDPR and CCPA much more manageable. Data integrity for sessions means more than just not losing records. You must preserve the exact chronological order of events, because that order defines the conversation. Over time, you also need a lifecycle strategy. Sessions shouldn't live forever. Clear retention and TTL policies let you automatically delete or archive inactive sessions, reducing storage costs and operational overhead while staying aligned with legal and business requirements. Every user interaction touches the session store, so performance is critical. Because runtimes are typically stateless, they reload the entire session history at the start of each turn, which adds network and serialization overhead. To keep latency low and throughput high, you want to reduce how much data you move and process. That's where history compaction and filtering come in, removing old or irrelevant details before they ever hit the model or the network. Modern LLMs can handle surprisingly long contexts, but they're not infinite. If your conversation history grows beyond the model's context window, calls will simply fail. Even before that, more tokens mean higher API bills and slower responses. There's also a quality issue. As you pack in more and more text, the model can get distracted by noise and accumulate autoregressive errors. So the challenge isn't just to remember everything. It's to remember the right things in a compact form. The paper compares context management to packing a suitcase for a long trip. If you try to bring everything, the suitcase becomes unusable. If you bring too little, you miss essentials. Compaction strategies are how you pack smart. Simple approaches include keeping only the last n turns or walking backward through the history until you hit a token limit. More advanced methods use recursive summarization, periodically summarizing older parts of the conversation and replacing them with concise summaries that preserve the important bits. In ADK, you can plug in context filters that limit what gets sent to the model without changing the underlying stored session. For example, a context filter plugin can keep only the last 10 turns plus the latest user query in the prompt. Separately, you can configure events compaction to periodically summarize older events after a certain number of turns. This lets you keep the full raw history in storage while feeding the model a compact, carefully curated view. A key design choice is deciding when to compact. Count-based triggers fire when the conversation exceeds a threshold in turns or tokens, simple and often good enough. Time-based triggers run compaction jobs after periods of inactivity, using idle time to clean up. Event-based triggers are more semantic. The agent decides to compact when it detects that a task, subgoal, or topic has wrapped up, which often aligns better with how humans think about conversation segments. Summarization and other compaction steps can be computationally expensive. To keep the user experience snappy, you want to run these operations asynchronously in the background. Once a summary is generated, you persist it so you don't pay the cost again. It's also important to track which original events are represented in each summary. That way, you can avoid sending both the raw events and the summary to the model, and you maintain a clear mapping between the compacted and full histories. Memory in this paper means extracted knowledge, not just the raw transcript. A memory is a distilled snapshot, a summary, a fact, an entity, or a preference pulled out of a noisy data source, like a conversation or a document. These memories are stored across sessions, so the agent can provide a continuous, personalized experience over time. There's a tight feedback loop. Sessions are the main source of new memories, and those memories, in turn, help keep future sessions compact and focused. A memory manager is a dedicated service that stores and retrieves memories. Crucially, it uses simple, framework-agnostic formats like strings and dictionaries instead of framework-specific session objects. That design choice makes it a natural bridge between agents built on different frameworks. Multiple agents, possibly written in different stacks, can all connect to the same memory store, contributing to and drawing from a shared knowledge base. This is how you get true collaborative intelligence across a heterogeneous agent ecosystem. Terminology can be confusing. Some frameworks refer to the session transcript itself as short-term memory. In this white paper, the authors draw a sharper line. Sessions hold the verbatim, turn-by-turn dialogue and working state. Memory is the result of processing that data, summaries, facts, and other structured insights. Keeping that distinction clear helps when you design systems that need both detailed audit logs and compact reusable knowledge. A robust memory system is what separates a simple chatbot from a truly intelligent agent. With memory, the agent can remember user preferences, past decisions, and important facts across many sessions. It can build on prior work instead of starting from scratch every time. That continuity unlocks deeper personalization and more complex workflows, making the agent feel less like a stateless API and more like a long-term collaborator. By this point, we can see three pillars of context engineering. Sessions capture the live, per-conversation state. Memory captures long-term knowledge distilled from many sessions and other data sources. Retrieval Augmented Generation, or RAG, brings in external documents and databases on demand. A well-designed agent orchestrates all three, pulling from sessions, memory, and RAG to assemble the best possible context for each LLM call. Memory generation is the process of turning messy, verbose data into clean, reusable knowledge. That might mean extracting key facts from a long chat, summarizing a document, or merging multiple similar memories into a single, consolidated one. Many of the same techniques used for session compaction, like summarization, are reused here, but with a different goal: building a durable knowledge base rather than just fitting into a single context window. When you extract memories, you don't just want the content, you also want to know where it came from. Provenance and lineage track which sessions, documents, or events produced each memory. This is crucial for trust and debugging. If a memory seems wrong, you can trace it back to its source. It also matters for updates. If the underlying data changes, you know which memories might need to be refreshed or deleted. During inference, provenance can help the agent decide how much to trust or prioritize a given memory. Just like compaction, memory generation needs trigger rules. You might extract memories after a certain number of turns, after a period of inactivity, or when a task or topic completes. You can also trigger memory generation when new external data is ingested. To keep the experience smooth, these processes usually run in the background, so the user doesn't wait for summarization or extraction before seeing a response. One powerful pattern is to expose memory operations as tools the agent can call. Instead of memory being a hidden side effect, the agent can explicitly decide to retrieve memories, write new ones, or update existing entries. This makes memory part of the agent's reasoning loop. It can plan when to look up prior knowledge, when to store new facts, and how to reconcile conflicting information over time. But treating memories is its own design problem. You can fetch relevant memories before building the prompt, or you can let the agent call a memory retrieval tool mid-conversation. Either way, you have to balance how many memories you bring in against the limited context window. Relevance scoring, semantic search, metadata filters, or task-specific heuristics helps you pick the most useful memories for the current turn. Once you've retrieved memories, you still have to decide how to present them to the model. Some memories, like user preferences, might be baked into the system instructions, so they always apply. Others might appear as part of the conversation history or as separate evidence blocks, similar to retrieved documents. Beyond factual memories, you can also store procedural memories, patterns of behavior or workflows the agent has learned, which can guide how it approaches similar tasks in the future. A memory system isn't set and forget. You need to test it end to end. Does the agent extract the right memories, retrieve them when needed, and actually use them to improve behavior? Over time, you should monitor for drift, memories that become stale, contradictory, or simply wrong. And because memories often contain sensitive user data, they require the same level of privacy, security, and governance as session logs, if not more. Stepping back, the story of this white paper is that stateful, personal AI doesn't emerge from the LLM alone. It comes from careful context engineering. Sessions give you a detailed per-conversation record. Memory distills that record into durable knowledge. Compaction and extraction keep everything efficient and within context limits. And by making memory framework agnostic, you enable different agents and frameworks to collaborate over a shared cognitive layer. Together, these patterns turn stateless LLMs into robust, long-lived agents that can remember, learn, and adapt over time.